If you recall, this week we've been looking at Taylor polynomials and Taylor series. Taylor polynomial is just an extension of the tangent line. The Taylor series is just an extension of the Taylor polynomial. In both cases, we just say, remember the tangent line? Yeah, just keep going. So we're making a description of a function based on matching derivatives at a point. Polynomial description of a function based on matching derivatives, just like we built the tangent line. Since the Taylor series is a power series, we care about the interval of convergence. These are the values of x for which the Taylor series works, is valid, converges. The ones that we looked at so far, e to the x, cosine x, and sine x, had intervals of convergence of all real numbers. And it's pretty clear because of that factorial in the denominator, the unchecked factorial in the denominator. We also had the power series for natural log of x near x equals 1. That had a limited interval of convergence. That was only valid for x between 0 and 2, strictly greater than 0, but less than or equal to 2. The idea is that the Taylor polynomial approximation is improved by writing more terms. Using a higher degree polynomial approximation, we get closer to the value of the function over a wider interval, and this works up to the interval of convergence. So we will get values that are closer, and the approximation will work on a wider interval. But this only goes up to the interval of convergence. When you have something like an interval of convergence of all real numbers, like we have for sine and cosine we saw yesterday, that would mean a lot of terms if you're far from here. So it might be a good idea to just shift things all over to where you are interested in, since you're trying to make a model of a periodic function. All right, we want to talk about the things that we can do with Taylor series. One thing we know is that Taylor series are power series, so all the things that we could do with power series, we can do with Taylor series, because it's just a kind of a power series. So if where they converge, we can add them together and we will still get a convergent series. We saw some things yesterday that we could do, that we just kind of guessed that we could do, and it seemed to work out pretty good. So let's review some of the things that we know we can do with Taylor series. First, we can integrate and differentiate by term. We can integrate and differentiate. So the derivative of sine x is cosine x. And if I take the derivative of the Taylor series for sine x, I should get the Taylor series for cosine x. And that's what happens. Excuse me. So we know that the derivative of sine is cosine. If I take the derivative of the Taylor series for sine x, I end up with the Taylor series for cosine x. Once again, let's review this whole factorial business. 3 factorial is 3 times 2 times 1. When we take the derivative, the exponent 3 becomes a coefficient and cancels out the 3. So when we cancel a 3 out of a 3 factorial, we still have 2 times 1, or 2 factorial. When we cancel the 5 out of a 5 factorial, we're left with 4 factorial. And we cancel the 7 out of the 7 factorial. I was thinking too far ahead. When we cancel the 7 out of the 7 factorial, that will leave behind a 6 factorial. So we end up with the power series for cosine. If we integrate the sine, we should end up with minus cosine plus some constant. We get a constant of integration when we integrate. So if I integrate all these terms, the integral of x is x squared over 2. The integral of x cubed is 1/4 x to the 4th. So I have a 1/4 x to the 4th over 3 factorial. And then a 1/6 x to the 6th over 5 factorial. And a 1/8 x to the 8th over 7 factorial. Then we notice what happens is we're adding the next value onto the next integer onto our factorials. So if we take 4 times 3 factorial, that's going to give us 4 factorial. 6 times 5 factorial is 6 factorial. 8 times 7 factorial is 8 factorial. We notice that we have the x squared, and we're missing the constant, but the constant happens, we're missing the 1 that we should have in a cosine, but that's part of the constant. So in that plus c is where we'll find the plus 1. And the signs are off, but that's expected because we should have negative cosine. So there's your 1 plus, and it should be, there's your 1, and there's instead of minus x squared over 2 factorial, we have plus x squared over 2 factorial. So I guess the minus 1 is in there. Two by itself is the same as 2 factorial. So we've got all the pieces that we're looking for. So one of the things that we noticed is that we can integrate and differentiate as expected. This is always good news when it works, when math works exactly like you think it would work. Number 2 thing that we can do that we did yesterday was we can perform compositions. We can use Taylor series in compositions. So if I have a function that looks like, if I want the Taylor series for e to the negative x squared, let's put it this way. We know that the Taylor series for e to the something is the sum as n goes from 0 to infinity of that thing to the n over n factorial. So e to the x is the sum x to the n over n factorial. If I have something else in my exponent, so if I have, for example, e to the negative x squared, I can just replace the x's with the negative x squareds. And now we have the power series for e to the negative x squared. This is useful because now we don't have to take all those derivatives. So we can avoid taking all the derivatives of e to the minus x squared by just plugging negative x squared into the known Taylor series for e to the n. We might want to clean this up so we can see what's going on. This minus x squared to the n, the minus 1 to the n will give us some alternating. So we're going to have some alternating from the minus 1 to the n. And x squared to the n will be x to the 2n. So we're going to have even powers over the regular factorial, and we're going to get alternating. So we'll have 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial. This is useful like we saw yesterday because e to the negative x squared does not have a nice antiderivative. That is, it is not the derivative of some finite combination of elementary functions. So to make an antiderivative, we have to break one of those two restrictions. We either have to use a non-elementary function, for example, constructing an antiderivative with the fundamental theorem of calculus, or we have to use an infinite combination of elements. When we negate an and statement, we just have to negate one of the pieces. Not A and B is not A or not B. Just need one of them. So we want to add to this. Remember the idea here that of the things that we're looking to do is so we can avoid taking all the derivatives. We don't want to take all the derivatives. That can get messy. And this is a math class. We're trying to avoid how to do all that math all the time. Unless you like taking derivatives. Maybe that's your thing. I don't know. Also in the category of let's avoid taking all the derivatives, we could put multiplication and division. This is just going to be the same algebra that we're used to, but it's going to be a little bit weirder because of that plus dot, dot, dot. So for example, if I have a function that is a product of, let's say, e to the x and sine of x. I don't want to take all the derivatives of e to the x sine x, and I have to do a bunch of product rule, and then some more product rule, and then some more product rule, and then some more product rule. It's going to be messy. But if we just multiply, I can take the power series for e to the x and multiply it by the power series for sine x. So we're just going to do the same thing that we always do. We're going to multiply these polynomials. Each term of one polynomial gets multiplied by every term of the other polynomial. And then we add up the like term. The same thing that we always do when we're multiplying. Each term of one polynomial by every term of the other polynomial. So each term of the power series by every term of the power series. Each digit of one number by every digit of the other number. Then you add stuff up. Same algorithm that we've always used. It's just weird here because of the plus dot, dot, dot. So we don't get to use FOIL because there's no outer and there's no last. There's the first and then there's a bunch of inner. So it's like, and it just goes on forever. But the idea is we avoid taking derivatives of e to the x sine x by multiplying the power series for e to the x, the Taylor series for e to the x, and the Taylor series for sine x. This is just a question of keeping track of stuff. I'm going to multiply everything by 1. So, or I'm going to multiply everything by 1. So 1 times everything in the sine x is going to give us an x minus x cubed over 3 factorial plus, oops, I'm going to end up with some even powers. So 1 times x is x, then minus x cubed over 3 factorial, leave a space, plus x to the 5th over 5 factorial, leave a space, minus x to the 7th over 7 factorial. I've already gone way farther than I intend to. So that's just multiplying everything by 1. So multiply by 1. Now we'll multiply everything by x. X times x is x squared. X times x cubed over 3 factorial is going to be minus x to the 4th over 4 factorial. X times x to the 5th over 5 factorial is plus x to the 6th over 5 factorial. X times x to the 7th over 7 factorial is minus x to the 8th over 7 factorial. And then there'll be some more terms. Now we go through and we're going to multiply by x squared over 2 factorial. X squared over 2 factorial times x is going to be x cubed over 2 factorial. X squared over 2 factorial times x cubed over 3 factorial will be minus x to the 5th over 2 factorial times 3 factorial. X squared over 2 factorial times x to the 5th over 5 factorial is going to be plus x to the 7th over 2 factorial, 2 factorial, 5 factorial. I'm going to do one more row. Oh, that's right. I only wrote 4 times. Now we're going to multiply by x cubed over 3 factorial. So x cubed over 3 factorial gets multiplied by x, and we get x to the 4th over 3 factorial. Then x to the 6th over 3 factorial, 3 factorial. Then x to the 8th over 3 factorial, 5 factorial. And my last one, x to the 10th over 3 factorial, 7 factorial. Now this keeps going on forever and ever and ever, but we have some stuff. I know what the first, second, third, and fourth degree terms are going to be. I don't know what the 5th degree term is going to be. We're going to have another row of 5th degree terms. I would need more, if I get more terms, I can have an x to the 5th term here, and then an x to the 7th term, an x to the 9th term, and x to the 11th term. And then, but the next row, the smallest term is going to be an x to the 6th. So at this point, multiplying the first 4 terms of e to the x by the first 4 terms of sine x, I get the first 4 terms of the product. And that gives me up to a first, second, third, 4th degree Taylor polynomial. So the first term is definitely going to be x. The next term is x squared. The next term is going to be minus x cubed plus x cubed over 2 factorial. So it's going to be a minus 1/6 plus 1/2 minus 1/6 plus 3/6 is 2/6 or 1/3. Then the next term will be a minus x to the 4th plus minus 1 over 24 plus 1 over 6. So it's going to be 4 24s. So minus 1/24 plus 4 24s. Minus 1 plus 4 is 3 24s or 1/8. The important thing to note here is the fact that we can even do this in the first place. And I just take these two Taylor series and multiply them, and it looks like the answer is yes. It's just going to be a matter of keeping careful track of our product. But the multiplication is just like the multiplication that we always. Any questions? Then if we have a composition, if this, instead of an e to the x, is e to the negative x squared, I can just plug in a negative x squared in for the e to the x, use that Taylor series, and then done the multiplication. I wouldn't be able to do it now because I'd have to do it beforehand, but The big idea is that we want to avoid doing all the derivatives because that could get messy. We're trying to avoid taking derivatives. The first derivative, if we start off with tangent, no problem. Tangent of 0 is 0. We don't have a term here. The derivative of the tangent is secant squared. No problem. We got the first derivative, secant squared. The derivative of secant squared is 2 secant times secant tangent. So 2 secant squared tangent. That wasn't so bad, but now I have to do the product rule with a chain rule inside, and it's starting to get bad. So let's try to solve this problem with algebra. Tangent is sine x over cosine x. So I'm just going to take the series for sine x and divide it by the series for cosine x. This is going to look awful and everybody's going to hate it. But we're still going to do the same thing that we always do with division. We're going to take the top, divide it by the bottom, and we're going to do this just with repeated subtraction. We're just going to use our repeated subtraction algorithm. I'm going to put my bottom, write down the denominator first. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Then there's some other stuff going on. I'm going to divide that into x minus x cubed over 3 factorial. I'm going to have an x. These are all going to be odd, so I don't need the spaces. When we're doing polynomial long division, we always start out, we're just asking the question, how many times can I subtract the denominator from the numerator without going negative? We're asking the same question. It always bothered me that when long division was described to me, I'm still programmed with this thinking. If I do like 3 into 715, the first question is like, well, how many times is 3 going to 7? Well, why don't we just ask the question, how many times is 3 going to 715? We're going to do it in part in pieces. How many times can you subtract 3 from 7 without going negative? And that's twice. It's the same question down here with polynomials or power series. How many times can I subtract 1 from x without going negative? To make that subtraction even happen, I have to subtract x times. X times 1 is x. X times minus 2 times minus x squared over 2 factorial is minus x cubed over 2 factorial plus x to the 5th over 5 factorial. X squared over, oh yeah, I'm just multiplying by x. I'm going to lose track. So I need to multiply by x to make the subtraction even work. So x times 1 is x. X times x squared over 2 factorial is minus x cubed over 2 factorial. x times x to the fourth over 4 factorial is plus x to the fifth over 4 factorial, and minus x to the seventh over 6 factorial. And then there'll be some more terms. And we are subtracting. The x minus x cancels out. That has to happen. That was the whole point of multiplying by x. That is the number of times that we could subtract the denominator from the numerator. That zeroes this part out without going negative. We have to figure out what this term is. I've got minus 1/6 plus 1/2 minus a 6 plus 3/6 is 2/6 or 1/3. And then we just have to keep going. And it's just more fraction stuff. 1 over 120 minus 1 over 120, 1 over 5 factorial. Minus 1 over 4 factorial. One over 5 factorial minus 5 over 5 factorial is minus 4 over 5 factorial. If we cancel out the 4, down here is going to be a 5, a 3, and a 2. So 1/30th. And now I'm just going to get more obsessed with the details. So then there'll be another term. Then we just go on to the next term. Now I need to subtract 1 from x cubed over 3 factorial, and I can do that x cubed over 3 factorial times. X cubed over, sorry, not 3 factorial, over 3. So x cubed over 3 times 1 is going to be x cubed over 3. X cubed over 3 times x squared over 2 factorial is going to be minus x to the fifth over 3 factorial. X cubed over 3 times x to the fourth over 4 factorial will be plus x to the seventh over 3 times 4 factorial. X cubed over 3, and then we're off the map at this point. So here there be monsters. And then we would just subtract. The important thing to note here is that we are running the same game that we always run. In the previous problem, we were just multiplying. It was just like super foil, but there's no outer and last, but they go on forever, so it's like FI. Here, we're doing the same long division that we learned back when we first did long division. How many times can we subtract 3 from 7? We can do that without going negative. We could do that twice. Really what we're saying is how many times can we subtract 3 from 700? We could do that 200 times. 200 threes is 600. And then we subtract 115. And then we start subtracting the 3 from the 11 and so on. The whole point of the algorithm is to subtract in pieces. Any questions? How's everybody okay? All right, so we know how to find Taylor series, and we know that we want to find more Taylor series by not taking derivatives. At this point, you'll probably just want to find the Taylor series for tangent by some other means that doesn't involve taking derivatives of tangent. I'm not sure exactly what we might try to do to find that, but gosh, I wonder what we're going to do. Oh, I scrolled off. Where is it? Oh, look there, series expansion at x equals 0. All right, so that's going to do it for today. That's going to do it for this week. I will see you all on Monday. Thanks for playing.